In this lesson, we're going to have a look at something called the SUVAT formulae, S-U-V-A-T. It's obviously not a real word, it is an initialism for some of the variables we've encountered already. So the S is obviously displacement, the U is the initial velocity, V is the final velocity, A is acceleration, and T is time. Okay. Now we're going to have a look at these formulae. This is how they're given to you in the formula booklet. There's a list of 5 of them here. So we've got V equals U plus AT, S equals UT plus half AT squared, S equals VT minus half AT squared, V squared equals U squared plus 2AS, and S equals half U plus VT. Okay, and I've described what those variables are already, but I'm just going to make a note of them here. So S is displacement, U is initial velocity, V is your final velocity, A is acceleration, and T is time. Now, depending on what your scenario is that you're looking at, you can obviously pick a different formula to help you solve some problems. So perhaps you know U, A, and T, and you want to find V, in which case you would use the first formula, and so on. It just depends on the information you've been given. Now, the one condition for using these formulae is that it has to be a period of constant acceleration. Okay, they're sometimes called the constant acceleration formulae. So A must be a fixed number. We can't have A changing all the time. Okay. So do bear that in mind with your questions. We'll talk about how to solve problems where we don't have constant acceleration, so variable acceleration, later on in the course. In fact, there's a whole chapter called variable acceleration, which we'll visit later on. Now, what I'm going to do is I'm going to derive these formulae from this velocity time graph that I've got here. So this is velocity here, and this is time on this axis. Okay. Now, on this graph, it obviously starts at some speed here, which I'm just going to call U for the initial velocity. And it reaches a speed up here at time t of v, its final velocity. Okay. Now think about the things that we know about a velocity time graph already. We know that we can look at the gradient, and that tells us the acceleration. And we know that we can look at the area underneath it, and that tells us the displacement. And we're going to use those to come up with these SUVAT formulae. So let's look at the gradient first of all. Okay. If I look at the gradient, that's the change in y. So the change in y is going to be v minus u, okay, because it's the height of this triangle here. So that's v minus u. The change in the x-axis is t. And that's equal to the gradient, which we've just said we already know from what we know about VT graphs already, that that is equal to acceleration. So I can say that v minus u over t equals a. And hopefully that makes some intuitive sense too. The change in velocity over time is your acceleration. And if I rearrange that, I get to my first equation, v equals u plus at. Now, for some of the other formulae, these involve displacement, so I'm going to look at the area underneath the shape. Now, one way of finding this area is to just consider it as a trapezium. So I remember the formula for a trapezium normally, if it looks like this, is half a plus b times h, where this is a, this is b, and this is the height. Now here we've got a trapezium on its side, basically. So we can say the displacement, so the area underneath the graph, is equal to half. Instead of a plus b, I've got this length here, plus this length here. So that's going to be u plus v. And then times the height, which is this length here, which is just t. And that gives us our second formula. S equals half u plus vt. So we've got this one here, and we've also got this one here. Okay. Again, let's think about the area. I'm going to split it up as a triangle and a rectangle this time, like that. And I'm going to find the area of this rectangle here plus the area of this triangle here. The area of that rectangle is just going to be u times t. So displacement, so the area under the graph is ut plus, well, this is a triangle, so that's half base times height. So that's half, the base is t, the height is v minus u. Okay, now that's not quite one of the formulae that I'm looking for, but it is pretty close. This last bit here, v minus u, well, if we look back up to here, v minus u equals at. That came from our definition of acceleration using the gradient. So v minus u is actually the same as at. So down here where I've got v minus u in a bracket, I'm going to replace it with at. And now I'm going to simplify this. So this is going to simplify to half at squared. Okay. And that's one of our other formulae. S equals ut plus half at squared. And that came from finding the area under the graph as a rectangle and a triangle. Now, another way we can find the area is by considering the big rectangle, so this whole rectangle shape here, and then subtracting this bit, subtracting this triangle. Okay. So the way that I could do that would be S equals, well, the big rectangle now, so the taller rectangles would be VT, and I want to subtract that triangle, and actually that triangle is the same size as the other triangle that we worked out a minute ago, which was equal to half at squared. So we can get this equation here, which is the big rectangle minus that triangle. And that gives us the next SUVAT formula, S equals VT minus half at squared. Now, there's one left, and we have to get this one algebraically. And we get there algebraically by combining this equation here with this one here. Okay. So I was going to write these down below. So we're going to consider v equals u plus at and s equals half u plus v t. And what I'm going to try and do is basically eliminate t, because I want to get an equation where I don't have to worry about t. So I'm going to rewrite this one. I'm going to rewrite v equals u plus at as v minus u over a equals t. And I'm going to substitute that into here. So that becomes s equals half u plus v times t, which I now know is v minus u over a, like that. Now I'm just going to rewrite this as v plus u, v minus u over 2a. That's still the same fraction. You might be able to see where this is going now. So that means that 2as equals v plus u, v minus u. Hopefully you recognise this is a difference of two squares. So this would be v squared minus u squared. And if I just finally rearrange that, I can get v squared equals u squared plus 2as, which is the final formula. And I've derived all of my SUVAT formulae. Okay, so we've got basically several formulae with a different combination of variables in each one, so that we can pick and choose which formula to use for our problem. I would suggest that you learn these 5 formulae, and if you've done enough practice, then you'll find that you just remember them anyway, but they are in the formula booklet if you can't remember them. But I would hope that by the end of the course you've done enough of them that you will remember them. So I'm just going to go through several examples, several different contexts, and show you how to use these SUVAT formulae. fact, I'm going to copy and paste the SUVAT formulae onto my page 2. Just so we've got them there. Okay. So it says a cyclist is travelling along a straight road. She accelerates at a constant rate from a velocity of 4 to a velocity of 7.5 in 40 seconds. Find the distance travelled in the 40 seconds. So let's just make a note of our variables. So from a velocity of 4 meters per second, so that means that u, the initial speed, is 4, to a velocity of 7.5, so v is 7.5. And the time that takes is 40 seconds. The thing we're trying to find is the distance, that's s. So s, I'm just going to write as s. Now, looking at the variables I've got, looking at the equations I've got, I think we can use s equals half u plus v t. Because I don't know what the acceleration is. So s is then half 4 plus 7.5 times 40. I can calculate s. It gives me 230 meters. Okay. And for part B, find the acceleration. So I've still got these same variables. U is 4, v is 7.5, t is 40. And we now know that s was 230. And we want to find out what a is. So I'm just going to write a as a. I'm going to use v equals u plus a t. I could use a different one now that I know the distance, but I'm just going to stick with v equals u plus at. So that means 7.5 equals 4 plus 40a. And I can solve it to find a. So that gives me 0.0875 meters per second squared. That's my acceleration. There we go. Let's have a look at another example. A particle moves in a straight line from point A to point B with a constant deceleration of 1.5 meters per second squared. The velocity of the particle at A is 8 and the velocity at B is 2. Find the time taken to move from A to B. Okay, let's just draw a little diagram here of what's going on. So this is point A, this is point B, and it says its deceleration is 1.5. So because it's decelerating, we can say that the acceleration is minus 1.5 because it's slowing down. At A, its velocity is 8, so u is 8. At B, its velocity is 2. We've got to find the time. So I'm just going to put t equals t. So we've got u, v, a, and t. So I'm going to use v equals u plus a t. And fill in the numbers. 2 equals 8, and then it's going to be minus 1.5 t. Solve it to find t. So that's 4 seconds. Part B, find the distance. So we want to find s. So I'm just going to write s equals s. We've still got u as 8, v is 2, a is minus 1.5, and I want to find s. So we could use v squared equals u squared plus 2as. So that means 2 squared equals 8 squared plus 2 times minus 1.5 times s. And then we can solve that to find s. Which gives me 20 meters. There we go. Okay, next part. After reaching point B, the particle continues to move along the straight line with constant deceleration 1.5. So it's still got this same acceleration of minus 1.5. The particle is at the point C 6 seconds after going through point A. Okay, so we've got point A, point B, and point C. We know that it was going at 8, then it's going at 2. We know that actually the time it takes to get to C is 6 seconds for the total distance. What else do we know? We know that A is minus 1.5. We know that this distance here between A and B was 20. Okay, I think that's everything we know. Oh, and we know that this distance took 4 seconds. So therefore this distance here must have taken 2 seconds. We've got to find the velocity at C. Okay. Well, let's maybe consider just B to C. So from B to C, the initial speed, if we just look at B, is 2. The acceleration was still minus 1.5. The time it took to go from B to C was 2 seconds. Okay, so we're just looking at B to C. And we want to find the final velocity. So we can use V equals U plus A T. So what's that? Minus 1. Does that make sense? Yeah, so that comes out as minus 1 meters per second squared. So our interpretation there is just that it is moving right to left rather than left to right once it goes through the point C, which is slightly odd, but there you are. For part D, find the distance from A to C. So on the distance from A to C, well, we've got lots of information to work with now. So let's go for the whole trip. So U is 8, A is minus 1.5. We know that the time taken to go from A to C was 6, and we want to find the distance. So I can use S equals UT plus half AT squared. So S is equal to 8 times 6 plus half times minus 1.5 times 6 squared. Which is 21 meters. Okay, so the total distance between A and C is 21 meters. Okay. A car moves some traffic lights along a straight road with constant acceleration. The car starts from rest at the traffic lights, and 30 seconds later it passes a speed trap where it is registered as travelling at 45 kilometers per hour. Find the acceleration of the car, first of all. So things that we know here, it starts from rest, so that means that U is 0. And 30 seconds later, it passes a speed trap where its speed is 45 kilometers per hour. I'm going to convert that to meters per second. So 45 kilometers per hour, I can do 45 times 1,000, because that's how many meters there are per hour. And then I don't want it in per hour, I want it per second. So I'm going to have to fuck's sake. I can't do that. I'm going to convert that 45 kilometers per hour. Okay, so that's obviously 45,000 meters per hour. So 45,000. And then I'm going to have to divide that by 60 to get per minute, and then divide that by 60 to get per second. So that's 12.5 meters per second. Okay, so I just want to use standard units here, really. So I've got V, U, and I just want to find A, and I've got T. So I can use V equals U plus AT. So 12.5 equals 0 plus 30A. So 12.5 divided by 30 gives me A equals 0.4167, if I round it, meters per second squared. Part B, the distance between the traffic lights and the speed trap. So we've still got the same information. U is 0, T is 30, V is 12.5. I could use A now if I wanted to as well, but we might be able to do it without. I just want to find S. So I could use S equals half U plus V T. So equals half 0 plus 12.5 times 30. So that's 12.5 times 15. So 187.5 meters. Okay. So it's all about just picking the appropriate formula depending on the information you're given. Sometimes picking out the information is the hard bit. Okay. So a particle is moving along a straight line from A to B with constant acceleration 5. The velocity of the particle at A is 3 in the direction AB. The velocity of the particle at B is 18 meters per second in the same direction. Find the distance A to B. All right, quite wordy, isn't it, this one? So let's just make some notes. The acceleration is 5, and at point A, the speed is 3. At point B, the velocity is 18 meters per second. Okay, and in both cases, they're moving in that direction. And we've just got to find the distance. So we want to find S. So we've got U, V, A, and S. So V squared equals U squared plus 2AS. And put their numbers in. Sorry that my 5s and S's look similar. Right, 18 squared minus 3 squared divided by 2 divided by 5. So S is 31.5 meters. There we go. So sometimes just a little simple diagram like that can help you think about it too. Okay. So a particle is moving in a straight horizontal line with constant deceleration 4 meters per second squared. So that means that A is minus 4. At time t equals 0, so at the start, it passes through a point O with speed 13, travelling towards a point A where O to A equals 20 meters. Find the times when the particle passes through A. Okay, well this is interesting because it says the times, it doesn't say the time, it just says the times. So let's see what's going on here. So we want to find the time, so we want to find t. We know A, we know U, we know S. So let's use S equals UT plus half AT squared. And I want to find the times when it's going through point A, and point A is 20 meters away. So that means 20 equals UT, so that's 13T plus half AT squared. So that's going to be half of A, so that's minus 2T squared. Okay. Now, if you look at that equation, that is a quadratic equation. So you would expect it to have possibly two solutions. Hence why we've got times rather than the time. What's going on here? Because it's decelerating, so it shoots off at 13 meters per second, then it gets slower and slower and slower and slower and slower until it reaches 0. But it's still, because the deceleration is basically pulling it that direction. Once it reaches a speed of 0, it then turns around and comes back this way. So there's one time when it goes through point A on sort of the outward journey, and then there's another time when it goes through A on the return journey. So we get these two different times. So all we're finding is when this quadratic curve, this blue line, meets this point here, displacement of 20. That's basically what we're doing algebraically. So let's move this all onto one side and solve it. Okay, and in mechanics, I'm more than happy to just use my calculator to solve any polynomial that comes up, really. So minus 2, 13, minus 20. So the two times are t equals 4 and t equals 2.5. Okay, those are the two times. Now the second question, find the value of t when it returns to O. Well, let's keep the other variables the same. So u was 13, a was minus 4. We want to find t. The displacement this time, if we're talking about when it returns to O, that's when it's back to the start, so its displacement is 0. Okay, because remember, displacement talks more about its position rather than how far it's gone. So it's back to the beginning, so its displacement is 0. And again, we can use s equals ut plus half a t squared. So 0 equals ut, so it's 13t plus half at squared, so that'd be minus 2t squared. And that one's actually quite a nice one to solve, isn't it? Because it's not a full quadratic, so I can just factor out the t. So either t is 0 or t is at 13 over 2. So that's 6.5. Okay, so obviously the t equals 0, well, that's when it starts at the origin at time t equals 0. Then it goes out all the way past A up to here, turns around and comes back, and that full journey takes 6.5 seconds. Okay, so the last one we're going to look at before you do some practice. A particle is moving on the x-axis with constant deceleration 2.5. At time t equals 0, it passes through the origin O, moving in the positive direction of x with speed 15. So it's moving in this direction with speed 15. Find the time between the instant when p first passes through O, so how long does it take from going through here, to when it returns to O. So again, because we've got a deceleration, this is going to be one of those ones that shoots off like this, slows down, and then starts to come back like this. Okay, so we want to find the time that it takes to do the whole journey, basically. The time from when it first passes through O to the time when it returns. So we know that A is minus 2.5, U is 15. We want to find T. The displacement when it gets back to the beginning is going to be 0, because it's back to the start. So we can use S equals ut plus half at squared. 0 equals 15t minus 1.25 t squared. Okay, so either obviously t is 0, that's at the start, or 15 minus 1.25 t is 0. So 15 divided by 1.25, which is 12 seconds. Okay, so 12 seconds is our answer here. The second part of the question says the total distance travelled by p in this time. So obviously it's useful to use the fact that displacement is 0 when you go back to the start, but that's not very useful if you want to measure how far it's gone. Now the way to find how far it's gone would be to find perhaps how far is it to the end, so to the point where it starts to turn around, and then double that. That would probably be sensible, I think. So let's do that. But how do we think about this point here? Well, this is a point where it turns around, so it's got a positive velocity here. Then maybe here it's got a velocity still in this direction, but a lot smaller. Yeah, here maybe it looks a bit like that. But it gets smaller and smaller until on the way back, it's now going this way, and it's getting faster and faster. So at this point here, we can say that the velocity is 0, because it's on the point of turning around. It's going from a positive velocity to a negative velocity. So that's v equals 0, and we can use that to help us. So we know that u is 15, v is 0. We want to find out how far away that point is, so I'm going to say that s is s, and we know that a is minus 2.5. So I can use v squared equals u squared plus 2as. So that means 0 is 15 squared plus 2 times minus 2.5 times s. And we can find out what s is. So we get 45 meters. Okay, so that means the distance from the start to the point where it turns around and comes back on itself is 45 meters. So therefore the total distance must be 90 meters, because it's got to go there and then back again. So it's 90 meters in total. Okay, so for your first set of SUVAT questions that you're going to have a look at, I'd suggest having a look at exercise 9D in the textbook. Make use of the work solutions as well to help you with SUVAT, so you can see what they've picked out as the variables and which equations they've used as well. Okay. And next lesson we'll have another look at SUVAT. We're going to look at SUVAT of gravity in the next lesson.